We now come to address inflation, which is de facto the standard theory of quantum cosmology today. It really started in 1980, where Alan Guth, physicist at MIT, came up with what he called a spectacular realization. There's a page from his journal at the time. Some of these ideas have been already discussed by others, but not known to Guth. And since then, many other people have improved the theory and added more to it. Well, the reason why everybody got so excited and why inflation has achieved such a great acceptance is that it solves three key cosmological problems which had no obvious solution before. The first one of those is so-called the flatness problem. Why is the universe so close to being exactly flat? The second one is the horizon problem. Why was cosmic microwave so uniform? We'll explain both of these in a moment. The third one is less obvious, and this is why there are no magnetic monopoles observable today, whereas many Big Bang theories predict that there should be copious amounts of them created in the early universe. Inflation also accounts for the observed power spectrum of galaxy clustering, and those are ostensibly fluctuations left over from an earlier phase of the universe. It also predicts the existence of a random cosmic gravitational wave background, but we're very far from being able to detect such a thing, and implies that our universe is just a small part of a much, much, much bigger universe. Let's tackle the flatness problem first. In Friedmann-Lemaitre models, omega always evolves away from unity. So if the universe was slightly negative curvature, it will become more so as it evolves. If it was slightly positive curvature, it will become more so as it evolves. A great illustration of that is shown in this diagram due to Ned Wright. It shows the density of the universe 1 nanosecond after the Big Bang. And it was 400-something sextillion and 16 grams per cubic centimeter. Add 1 more gram per cubic centimeter, universe becomes closed and will collapse. Subtract 1, and the universe goes to expansion forever. So this is extremely sensitive. Even the slightest deviation of omega equal 1 from the early universe would map into a much bigger deviation today, and yet we know that the universe is very close to flat. So it must have started really, really close to flat, if not absolutely flat. The horizon problem can be stated this way. At any given time, you can receive signals from points that are within the time elapsed from the Big Bang. And the particle horizon distance is 3 times speed of the light times the age of the universe at the time. Now remember that early on, scale factor goes as time to the 2/3 power. And so it means that the horizon expands faster than the universe, and as time goes on, you get to see more and more objects come into it. Now look at cosmic microwave background. It originates from roughly redshift 1000. And so its temperature back then was about 4.5 powers of 10 higher than it is today. At that time, the horizon distance was given by the formula that I just mentioned above, and since then it's expanded by a factor of 1000. However, our horizon distance is bigger than that. And therefore, there should be many causally disconnected regions in the sky, which were not in a causal contact at the time that microwave background was released. So even though we can see that as one sky now, back then, patches of microwave background sky that are more than, say, 2 degrees apart were not in a causal contact. And yet, cosmic microwave background is uniform to few parts in a million. So how did these independent pieces of universe know to have same temperature within a part in a million, universes with which they could not have had physical contact? The monopole problem is somewhat generic to the particle physics, and prediction is that copious numbers of those will be generated during the grand unified theory phase transitions. Yet none have been found despite many intensive searches. Not only that, but their masses are supposed to be so high that coupled with their density, they would totally dominate dynamics of the universe. A generic expectation is that future theory of everything that unifies gravity with other interactions, all interactions were unified into one around Planck time or thereabouts. The universe undergoes a phase transition. Then the universe undergoes a phase transition where gravity splits from the other forces, and things remain roughly the same on a logarithmic time axis by almost 10 more powers of 10, when there is another phase transition. What is postulated here is that physical vacuum was not in its actual ground state at the time, but it was at a higher state. Just like in atoms, there is a ground state, and then electrons can go to higher orbits and have excited states. Also, supposedly, universe, the physical vacuum itself, could have been in such a higher state. Somehow, and mechanisms for this are very complex and beyond the scope of this class, the vacuum undergoes a phase transition going to the actual ground state, the true vacuum. And in that process, vast amounts of energy are released, and that energy is used to drive exponential expansion. Here is one schematic way to show it. Potential energy of some scalar field, phi, is plotted against potential itself. And if universe is at the center of the high plateau at 0, this is a metastable state. It will eventually roll down into the true vacuum, which is at some finite value of phi, and may even slosh around a little bit. So in this schematic, the universe rolls down the scalar field potential. So the decay of the field reheats the universe from that excess energy. And all of the matter energy content of the universe can be created in that process. So the universe undergoes phase transition and releases this latent heat, inflating exponentially. This could be just one of the many, many bubbles in a much larger universe that expand and maybe collide, which is a process called reheating. However, this is something that has never been observed yet. Now, the energy density of the physical vacuum can be described as a cosmological constant. This is not the cosmological constant of today, but some much larger value from the early universe. In that case, the Friedmann equation is given fairly simply, and it has an obvious solution, an exponential expansion. It turns out that in these inflationary models, this exponential expansion phase goes for about 100 e-folding times, or 40 orders of magnitude in size. And since the deviation of the density parameter from unity also goes exponentially, that means it was incredibly finely tuned to be close to unity to begin with. So here is a schematic expansion diagram. It's plotted as 1 plus redshift rather than 1 over that quantity, which would be the scale factor. So there is a rapid initial expansion, and then universe enters into a traditional Friedmann-Lemaitre phase. So how does this solve the flatness problem? Well, think about this as follows. You can start with a region on a sphere, where this is now a two-dimensional equivalent of four-dimensional space-time. And if you inflate that sphere by a large amount, that region will appear spatially flat. And by the same token, this great expansion of the universe essentially flattens the local curvature, which might have been more substantial. So the density parameter differs from unity by an epsilon, a very tiny number. At the same time, this solves the horizon problem. Space can expand faster than the speed of light. So the regions that were causally disjoint at the time of the recombination might have been spatially close to each other at the beginning of the inflation. They might be really adjacent to each other, and that's why they have same energy density or same temperature of the microwave background today. The inflation carries them apart, and so by the end of the inflation, they were no longer in a causal contact, but nevertheless, prior to that, they were nicely thermalized. Inflation also tackles the origin of the large-scale structure we see. In quantum physics, the vacuum is not empty, but it's populated by virtual particle-antiparticle pairs that appear and disappear, subject to the uncertainty principle. They cause essentially quantum fluctuations of energy density in the early universe. Now, inflation blows up these minute quantum fluctuations of physical vacuum to enormous size, where they can be really seeds of the large-scale structure that we observe today. It's a remarkable prediction that tiny quantum fluctuations can result in larger structures that are observed. And there is a specific prediction of the functional form of the power spectrum of these fluctuations, which turns out corresponds fairly closely to what's observed. Note that this is not a proof of inflation, because one can come up with different ways to reach the same observed state of large-scale structure, but the consistency is certainly very encouraging. Next time, we'll talk about even earlier universe.